Hello everyone. Welcome to the EasyPower Refresher webinar series. Today we're starting a four-part topic called an Introduction to Protective Device Coordination. And in many ways I consider this the most important installment of this series because the better you understand the basics, if you're a beginner to the topic, the better you'll be able to pick up the information in the following episodes. So welcome to all. And as we are in the habit of doing, we'd like to start with a poll question. No obligation or liability. So the first question is, how long since coordination was checked or updated in facilities that you're familiar with? This could be yours or clients. No obligation or liability, just strictly trying to get some feedback on the perspective that the audience is coming to the topic. I depend on this feedback a lot because it'll help me understand which areas to emphasize and a little bit more about the situations you're facing when you're out with clients. So it looks like we're almost to a quorum. Let's leave this open another 10 seconds. Appreciate your attendance and appreciate your involvement and participation. We supply a certificate of attendance via email for everyone that's attending, and we rely somewhat on the poll participation to verify that you're with us. So looks like we have a quorum. Here's how folks have weighed in on this question. So it looks like a pretty broad spread, like a bell curve, and I think this is pretty typical of the industry. So the second question is, has your facility experienced transformer or other equipment failures due to improper coordination? This is always a surprise to me because we get some real varied responses. Very frequently, people are attending because they have experienced or seen failures in somewhat catastrophic proportions. So it serves to validate the reason for having this topic in this series of presentations. So we got about 10 seconds for a quorum. Again, please participate. No obligation or liability. Strictly just trying to get a fix on where the audience is coming at the topic. Okay, here's how folks have weighed in on this one. It looks like it's 50-50, probably or certainly having experienced failures and then none reporting. Excellent, thank you. So we've divided the four-part series up into these quantum steps. Today we're going to be talking about basic concepts, spending a lot of time describing what TCC curves are and what their function is and how much information, if you understand the basics, can be gleaned. The next week we'll do the fuse protection. Week after that, I started getting into the breakers. And then finally, in the fourth week, we'll get into relays, generator protection, and system coordination overall. So, as I mentioned, I want to spend a lot of time on the basics and making sure that folks understand the TCC plots and how valuable are, how much information there is that can be gleaned about your particular situation. I encourage questions of all kinds, but frankly, my preference is to stay with the beginning questions or people that are honestly trying to learn from the ground up. And if more advanced questions come in, I may have to table it or highlight it when we get to topic in later episodes. We will be referring to EasyPower a lot. And so if you're familiar with the tools, you may want to follow along. So protective devices are in the circuit to prevent excessive temperatures in both conductors and equipment. They have the potential of minimizing the equipment damage, reducing the risk of fire and explosion, and potentially even reducing the risk of arc flash or other hazards. Frequently, they're required to meet legal requirements and insurance requirements. Now, the topic or the subject selective coordination has a specific meaning, and that's where we're kind of looking for in this series. And it requires the examination of the system's characteristics to determine the optimum device settings, coordination protection of the components and the circuits to achieve minimum circuit interruption for different types and magnitudes of faults and overcurrents. Selective coordination is obtained when a minimum amount of equipment is removed from service for isolation of a fault or other abnormality. So the catch-22 in this whole discussion is oftentimes selective coordination will result in higher incident energy, arc flash results in the downstream elements or even the upstream elements, because you'll see what we're doing is we're slowing down the system protection and the higher levels of the one line to be able to get the coordination. Interestingly enough, coordination is not required by the National Electrical Code except for critical or emergency related loads. And when we talk about coordination, we can look at a typical radial system when we see we have three levels of protection. There are the feeders, feeder breakers, the main breaker, and then the primary fusing on a main transformer. Now, if we have a fault on any one of the downstream loads, that fault current is sensed by all three levels of protection. And so at any point in time, any one of these three devices can protect the system from the fault. And they're there for specific reasons. For instance, the fusing is primarily to protect the transformer. The main breakers protect the whole system for the switchgear or the panel board. And then the feeder circuit is primarily protection from a fault downstream. So ideally, that's the breaker that we want to trip to prevent losing other parts of the system that aren't necessarily affected by the fault current. And the tool we use to do this is called a time current characteristic curve, or a TCC. And it turns out there are TCCs defined for virtually every element in the system. And we're going to be examining some of these. So there's TCCs for transformers, motors, cables, generators, any kind of protective device, capacitors and filters. And the shape is determined by the datasheet parameters from the manufacturer. So when EasyPower plots a curve, which we have some examples here on the right, it's because we are relaying information that the manufacturer provided on the datasheet for that element. Now, again, don't be afraid of this if you're a beginner. This TCC curve has some common characteristics. First of all, time is on the vertical axis, and this is a log-log scale. So when we look at 0.01 seconds, which is the bottom rung, then we get to a tenth of a second, 1 second, 10 seconds, and 100 seconds. So in a very short space, we can express a large variation in value. Likewise, on the horizontal axis, this is current. And in this case, we're referencing current in the 208 volt realm, which is the lowest voltage on our one-line diagram, the inset. And what the purpose of this is to give us the ability to establish some fault current. Based upon that fault current, determine what the trip time of each of these succeeding breakers is if the current were to be felt by that device. Now these are inverse curves, which means the higher the current, the lower the response time, or the quicker the trip time. So let's say during our short circuit analysis, we calculated the fault current at this bus to be 5,000 amps. So we plot a line at the 5,000 amp range. Again, this is current times 10 on a log scale. So where this is 100, that means it's 1,000. Where this is 5, that means it's 5,000. And so that fault current establishes a stress on that protective device. Now this gray plot is a typical TCC for a molded case circuit breaker. And it's magnetic and has magnetic properties and thermal properties. So thermal property is related to long time faults, and the magnetic is related to instantaneous response to very high current. The reason there's a thickness to the plot is that the manufacturer has a certain variation in yield, and what he's telling us, what they're telling us, is if we have a fault at this level, the sense and the breaker may trip anytime during this gray band, but he guarantees the breaker to trip at the upper right hand edge. So if we apply 5,000 amps to this breaker, we can see the manufacturer tells us it's going to trip in 20 milliseconds. Now if that current is sensed by the blue curve, now this is a typical plot for a low voltage power circuit breaker, which has more adjustments to it. And you'll see when we get into breakers, these the performance TCC can be varied considerably at each one of these bends in the golf club. But it's the same principle in that the breaker starts to sense the fault at the lower end of the plot, and at the upper right hand corner, edge of the plot, is where the manufacturer tells us it will clear the fault. So if 5,000 amps was applied to this breaker, we see it's about 300 milliseconds response for the low voltage power circuit breaker. Now, the current going through the transformer will be different on the primary side than it is on the secondary side, but the TCC and the EasyPower representation of it tells us what the primary current response time is for the element which is represented by the rust colored band. And this is a fuse, a typical fuse TCC. And what it tells us, if we apply the primary current for a 5,000 amp fault on the load, that the fuse will clear in approximately 80 seconds. So in this case, we have coordination, because if we have a downstream fault, the first element to respond is going to be the molded case circuit breaker. The second element, if for some reason the fault isn't cleared by the MCCB, would be considered by the low voltage power circuit breaker at 300 milliseconds. And then worst case, if the fault's not quenched, by the time the fuse limit gets to 80 seconds, and it will be cleared. So that's a lot of information that can be derived if we know where to look and where to place all these plots. So we're going to talk a little bit about transformers. Transformers need to be protected against overloads, and they have the potential of having internal faults, specifically from heat damage or mechanical damage if they're hit with too high a current. What they need protection from, and these are basically addressed by design characteristics and are represented in the TCC as we get to it. Through faults, though, are a function of external protection. And so transformer damage curves only deal with through faults, not internal faults. If you have an internal fault, then the transformer is already damaged, and all bets are off as far as the discussions of protective devices. So again, what we consider to be a through fault is an external fault on the secondary of the transformer itself. The windings see very high current. For instance, with a 5% impedance transformer, the full load current will be 20 times, roughly on an magnitude of 20 times the secondary. The secondary will be 20 times that of the primary. And that high level of current creates heating and magnetic forces that are a squared function, so they could be 400 times in the secondary versus the primary times. And these are levels that the transformer needs to deal with in normal operation. So through-fault damage can be the result of overheating and windings due to high current for a long period of time. Mechanical damage is due to the magnetic forces. When you hit the windings with high current, they repel each other, and the mechanical damage is cumulative. And you'll see when we get to that topic that the result is what's called frequent faults. And so the transformer needs to be designed with protection to a certain level, and we'll get into how they define that. ANSI C57 has transformer damage curves. I was corrected here recently that this is co-labeled. The IEEE versions of C57 has been updated. And transformer damage curves that define the magnitude and duration of the through faults of a transformer that it should be able to withstand by design. So here's how it looks. If we plot the transformer damage curve on a TCC, or the TCC plot, we see this line, which is referred to as the 100% damage curve of this particular size and impedance transformer. The tick mark at the top shows us the full current, full loaded current, and based upon what, and I don't have it shown on the bottom of the screen, what voltage we're referencing, this could be the primary current or this could be the secondary current. So the bottom line is, if we have a circuit that has, let's say, well, I cut off my legend here, 10,000 amps, the system should be able to run, the transformer should be able to run with 10,000 amps in the secondary without any damage. It's when we start to get to 100,000 amps that we need to be concerned about damage curves, and that's where the intersection between whatever our fault current level is and the damage curve needs to be observed. So again, the dotted line, at least in the EasyPower representation, is the 100% damage curve. So at no time did you want the transformer to be exposed to current higher than that level for this amount of time. Lindy's asking the question, should we calculate arc flash incident energy for both upstream and downstream of the transformer? Well, frankly, the answer depends upon whether you're going to have workers in the area. The requirement of IEEE 1584, NFPA 70E rather, is if anyone's going to be in the area, then their exposure to arc flash needs to be calculated. So it depends on your situation. Okay, so again, 100% damage curve is what we're focused on. The thermal damage curve, the thermal section of the curve, is the upper part, which is longer time at a little bit lower current. And so for current as low as, I'm guessing here what my scale is, 5,000 amps, we want to limit the time that it's exposed to the transformer to 600 seconds, if you understand what I'm pointing at here on the plot. Then the bottom part of the curve, where you have higher current for shorter amount of time, this is the area where you produce mechanical damage. Now, one other point on this plot is this little dot down here that's labeled inrush. Any protective device on the primary side needs to be sensitive or aware that you don't want to trip during inrush. So you don't want a protective device like a breaker or a fuse or a relay, for that matter, to be in the circuit and sensitive to this amount of inrush, which means our trip curve, when we go to plot it, has to be on the right side of the inrush plot. We'll go over that a couple times later. Now, I mentioned ANSI C57 or IEEE C57 defines categories between single phase and three phase and what's allowed as far as frequent faults. So category 1, which are the smaller transformers, there's no such thing as a frequent fault reduction. Category 2, which is mid-range, we're allowed 10 frequent fault excursions. And above 5,000 kVA, we're only allowed 5 excursions. So what that means when we plot the TCC, or when we're looking at the TCC, is that we apply this offset in the lower portion of the curve. Again, this is for through faults, but we're allowed, as long as we don't exceed the 100% damage curve, which again was a straight line, we're allowed the frequent fault excursion number for the life of the transformer. So for Cat 3 and Cat 4 transformers, we're allowed at 5 excursions, and consequently the design is meant to handle that. And ANSI C57 is for oil filled. It defines the frequent fault versus infrequent fault, mechanical damage, and the protection that's required. I was going to show EasyPower. So looks like this is my Z curve. These are referred to Z curves just because they kind of have a lazy Z look to them. So when I've set up different category transformers and I go to coordination and EasyPower, I want to plot what the frequent fault area is on each one. I can see for category 1, there's no frequent fault design. So all I have to protect or consider is a 100% damage curve. For category 2, which I think is allowed 10, then this is the area, as long as we don't exceed 100%, that we're allowed excursion of this particular current. Now, if I want to be conservative, I would protect my system so that I'm not intentionally allowing the current even to exceed the frequent fault. So that's a consideration that is probably taken into account by most designers. And then category 3, I'm allowed 5 excursions of the frequent fault. And you'll notice, just as an aside, we have, right now we're looking at the 480 volt scale, so we're 100 times the current. And so Cat 1, if I hover over this tick mark, look down at the bottom edge of the screen, and you'll see the coordinates of my cursor. So if I hover over the Cat 1 tick mark, you can see its maximum 480 volt current is 151 amps for 814 seconds. For the Cat 2 full load current, it's 1370. And for Cat 3, looks like it's 6532. Now again, that's that's the secondary current in the 480 volt range. If we want to reference and look at the primary current for full load, I right click and set as a reference this bus for TCC scaling. It moves all my TCC plots over, and it doesn't change their reference, but it changes the scale down here. So now we're in the 13.8 range. And if I hover over the tick mark for full load current, I can see for my Cat 1 is 5.21 amps and 13.8 volts. Cat 2 is 40 amps, 40.8. And Cat 3, can everyone see that? 238 amps for 841 seconds. So that's the full load current. Now these become important when we start to set protective devices, because the standards will reference some percentage multiplication of the full load current setting. So we'll get into that when we talk about protection. Okay, so protecting delta Y transformers is a little bit tricky in that the per unit current seen by the primary protection is not the same as seen by the secondary winding. And this is a little bit more obvious when we do a visual of the phase shift. But winding damage on through faults is a function of current through any one winding in the primary. So we must adjust the damage curve or the primary protection curve to compensate. And what I mean by that, we're looking at a delta Y transformer, and if we have a fault on the secondary side, that 1 per unit fault is sensed by just one phase or is amplified by one phase in the delta side. The total current, if I'm doing a phase-to-phase comparison, will be the same, but the individual phase. So if I'm doing phase protection, and specifically this becomes a concern where a single line to ground fault exists. If I'm doing primary protection for a single line to ground fault felt on the secondary side, then I need to be setting my current trip point at 58% of that 100% damage reference point. So ignoring load current, the primary relay or fuse will only see 58% of the current in the secondary windings for a ground fault on the secondary side. Now again, this applies only to ground fault protection when we have the protection on the primary side. So the ground is on the secondary and the protections on the primary. So that's what this solid line is in my TCC plot. And it's adjusted for the ground fault as seen from the primary. So let's see if we can stomp on this one. And I'm looking for ground current 01B. Now this is a little hard to conceive as a first, if it's the first time you've heard it, but it makes a whole lot of sense once you see it in a real circuit. So again, we have the potential for 3 different configurations: high resistance grounding on the neutral, hard ground on the neutral, and then no ground on the neutral. And if I go, and we have primary protection of a 40 amp fuse. So if I go to short circuit, I'm sorry, if I go to coordination, do I have it here? Yeah. So let's look at the hard ground, which is a typical setup usually. So again, we have our 100% damage curve, we have our derating curve, and then the frequent fault of each. If we have a fault on this bus, that's a single, I'm up here on the top row, it's a single line to ground fault. Each phase will see 42,194 amps, which is this tick mark here. If I look at, and we've got this clipped at momentary current. So right now, this fuse protects the primary and secondary from a frequent fault or a non-frequent fault. So this would be considered a conservative fusing, if you will, because it has healthy protection for both 100% damage and 58% reference on the primary. Now, you might say, well, how about all this extra room? What's going on? I've got more capacity that I'm not using on the transformer. So if I move my fuse to the right, the tool will, if there's a value in the library that has a different value for the same family, I can move it to the right and pick up additional capacity from the transformer without endangering my frequent fault on a single phase. ground fault. Now, let's see how far it'll go. If I picked out a fuse that's say 140 amps or size 140, this would have virtually no protection for a single line to ground, although I'm protecting the frequent fault area for a three-phase through fault. So this would be bad, if you will. Make sense? All right, let's look at another one. If we have no ground, then there's no ground fault to sense. And so even if I apply a single line to ground fault here, there's no ground fault anywhere in my system, either on the primary or the secondary. And so there's nothing to plot and there's nothing to sense. And if I go to the high resistance ground, now there's no second curve here, and that's because my current is so low, I'm limited to 100 amps protection on the secondary because of the resistor in the neutral leg, the ground leg, is limiting current to 100 amps. So that means primary-wise, I only have 2 amps, and that's way over here on my log scale. And so it doesn't make any sense to worry about default current on the primary fusing. Does that make sense? Now, three-phase fault doesn't change anything. If I have three-phase fault, my fuse will pick it up, and I have frequent fault protection. I'd be a little bit concerned about this low current, the lower fault current, for a longer period of time. And frankly, I probably rely on secondary protection to protect that part of my damage curve. Okay, let's move on. Close these out. One of the things I'm trying to show is how much information is there. And so if you know how to answer the question, it's worth playing with some of these curves and applying different faults and different conditions to the display to see what you get. All right. Okay, so we've kind of exhausted that. Now, the National Electrical Code sets recommended protection for transformer overcurrent protection with this chart, which shows primary protection for the primary side of over 1,000 volts and secondary of under 1,000 and over 1,000, over and under. And then for 6% and less, with breaker protection on the primary, we're allowed to go to a maximum of 600% of the full load current. With fuse protection, the recommendation is to go only to 300% or 3 times the full load current on the primary. On the secondary side, over 1,000 volts, we're allowed or suggested to go to 300% with a breaker and 250% on a fuse. So these are limits, a maximum protection. They're not recommended, and they're somewhat subjective as far as what you're trying to do with the design. So let's see what this gives me for over 300%. So what they're saying, what they're talking to me, why does the secondary ground fault? I'll just get to that question in a second. All right, so here we have Cat 2 1000 kVA greater than 1,000 volts primary, less than 1,000 volts on the secondary, and at 6%. So I think that gives us 300%. We're recommended to go as high as 300% protection. So let's see what we've done with a size 50E fuse. Of course, I have to select some stuff to plot the TCC. Now what this is showing, and the question is the fuse adequate for protection? So if we have a fault downstream, we see several things show up as I fault this bus. The maximum load current, let's reference this bus to be the 13.8 reference. If I hover over the FLA tick mark, I see our maximum current for full load is 42.8 amps. So 300% times that would be 120. So if I have a fuse, if I look again at my coordinates, if I have a fuse at this point, it's giving me 130 amps protection, which is just on the hairy edge of the 120. The NEC says I can pick the next value up if I don't have the value of 120. If I look, so I've got 40E gives me 114. So to be a little on the safe side, I'd pick that lower value. But what I'm looking for is it gives me 100% protection for my 100% damage curve, and actually pretty decent protection for a single phase to ground fault on the primary side. Again, I have some exposure here on my single line to ground fault that I would want to make sure I'm protected with some secondary protection downstream. Ovide says, why have secondary ground fault instead of primary? Well, it depends on the load. So if you have grounded systems and the secondary side, you can have very high fault current with a hard ground on the primary of the Y. I guess if you're saying, why not do secondary ground? The answer is probably it's a good idea to have both, because the transformer is so valuable or so costly. You want to make sure you're protecting it from a through fault. So if I have a ground fault, let's look at a single line to ground fault on the primary side. Excuse me, on the secondary side. I've got 21,000 amps in the phase that's grounded, and I have exposure now on the primary protection. So I need to consider how I'm protecting the transformer for a single line to ground fault. So Ovide saying, yeah, Mike is too. How about the inrush? And that's a concern. So I would probably want to take the next larger size, which puts me there, which exposes me even more on my single line to ground fault for these lower currents. But the point I'm trying to make is it's all available on the TCC chart, and you can make those decisions or have that discussion based upon the data that's coming from the manufacturer. Good point. So yeah, it's not a good idea to cross the inrush. All right. Yeah, I guess I've got ahead of myself. All right, so the transformer primary protection must provide right through of the inrush. The inrush is somewhat an arbitrary plot, and you can adjust this in the transformer setup, but typically you assume 8 to 10 times the full load current for 1/10 of a second, and it's based on the self-cooled rating, not on the forced air-cooled rating. And so I want to show where these are set up in the EasyPower. So if I come back here to the transformer icon and double click on it, I could open the dialog box for the transformer. And it's these check marks under impedance that determine which plot is made. So if I want to show my frequent fault curve or not, I check that box. Let me kind of move this over so we can see it. And as I apply, it takes off my frequent fault curve, the jog and the Z. If I want to not plot the unbalanced derating, which is a single line to ground fault, it puts me back to the 100% damage curve. So again, this could be considered a way to make a little bit more readable based upon what you're trying to examine. Now, the magnetizing inrush is based upon 8 times the full load current, in this case in 6 cycles. If we make adjustments, the manufacturer can tell us if this is a conservative value or if there's a value that's more specific for that transformer. EasyPower puts in kind of these typical values that can be modified. So all this is on the TCC curve, and it's based on the impedance and the full load, the ampacity rating, kVA rating. Okay, so the point I wanted to make is that transformers, because they're the most costly, usually the most costly single element in the system, deserve a lot of attention as far as protection and concentration on where the protection lies, whether it's in the primary or the secondary, and what part of the curve, what part of the TCC we're actually being sensitive to. So better protection. Crossing the inrush curve is not good, so maybe this is not the right fuse for this ultimate protection. And we're limited by the shape of the fuse the manufacturer gives us. That's the reason, and you'll see this when we get into week 4, relays give us a lot more versatility because they can be programmed more precisely than a fuse. Now I want to emphasize that all elements, most elements in the one line have TCC plots. And so here's a typical plot for a motor. The motor, based upon the horsepower and the X over R, has a plot that looks like a chair. And I refer this to a chair frequently. And what we see from this plot are a bunch of data. For instance, this vertical section, this is the full load current that the manufacturer predicts for the 100% loading running at full speed of the particular motor. Then this stubby curve horizontally, this is the acceleration, the crossover from the locked rotor current, which is calculated during acceleration, to the full load current for up to 100% speed. And then for a locked rotor, while the motor's accelerating, this vertical line tells us how much protection we need to provide, or at least we'll be sensitive to. So, and then the little tail on the bottom is a function of the asymmetric offset of the magnetic effects of the motor starting with across the line voltage. So I usually refer to the fact that on the left-hand side of the chair, this would be considered a normal start for any plot that's time and current specific. So if we take a reading of the motor current at, let's say, 200 seconds up here, and it falls anywhere less than the 100 amps, which looks like it's maybe 80 amps. I take that back. maybe it's 8 amps, that any current in that range at that time would be considered a normal start. Now, if it's to the right side, a time current plot to the right side, the that is considered a potential bad start, and so we need to have protective devices come into play. Now, this short stubby line, this is the thermal damage curve that any time current plot above and to the right of this plot, of this straight line, could potentially cause mechanical damage due to the heat. And it's one of those things you just don't want to let the motor achieve or be experienced to that type of current. So let's look at 1C motor TCC. So again, this is all determined by the characters, the parameters we've loaded in when we modeled the motor. And if we look up the setup for a 50 horsepower motor, we've typed in the horsepower, then calculate the X over R. And then the TCC is plotted by these typical values, again, any one of which can be modified if you know the specifics for that motor. And then once we plot the TCC, go to coordination, plot the TCC, and there we have the parameters that we were talking about. Again, full load current is at this level, looks like it's 60 amps, 61 amps. Locked rotor current looks like it's 388, and then the asymmetric tail potentially would bump it up to 448. Again, all this information is on the TCC, along with the thermal damage curve. And then finally, I want to point out that cables have a damage potential, that current for a given amount of time can cause heat damage, and so you want to make sure you have plenty of room between whatever protection for that element downstream and even its current carrying capability of the cable. So let's try that. Again, that's why it's important to make sure you have the parameters for a given system correctly recorded during data collection. So one more TCC. Again, we got two different cables. Let's plot them. And what we're seeing here is the fuse that's protecting some downstream load. We have two cables, and if we have a fault on any individual one, we see the damage curve for a fault at this bus is 37,000 amps, and the fuse would clear that a long time ago, instantaneously, within a half cycle. Likewise, on this side, the fault current's lower, but the fuse is still going to protect the cable. Okay, so I beat this topic of TCCs to death. Next week, we're going to talk about fuses and their impact on series rating and how to coordinate with fuses. And we will touch on the MCC relationship, although we'll cover that in more depth on the third week, and talk about the NEC Selective Guidelines that were part of the most recent NEC update. Appreciate attending today. By all means, check out the website for other webinars. If you have questions on any of this, on a project you're working on, I support contacting tech support at easypower.com, and they'll help you out. Hope you have a good day. We'll talk to you next week.